Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at vectors and lines. So in this first example, we're going to find a vector equation for the line passing through this point and this point. So it's very hard to draw the three-dimensional axis on my flat 2D screen, but I'll have a go at plotting these points. So it always goes x, y, z. So for A, it will be here at x equals -1 and y equals 2 will be over there. So this has a z coordinate of 0, it won't go up at all. Now let's try B. So that has x coordinate 2 and z coordinate 1. So we go across to x coordinate of 2. There's no y coordinate, so we're not going to come out this way at all. And then we're going to go up to z equals 1. So this z coordinate is going up, so think of it as heading out of your screen. So this point is like higher than this point in 3D space. So we're looking for the vector equation of a line that goes through those 2 points. This is a 3D line. So basically, we want to calculate an equation that will yield a vector that lies on this line. So to come up with such a vector, basically what we want is a vector that goes from O to A and then in the direction from A to B. But we don't want that vector to necessarily end up at B. We want it to be anywhere along this line. So we're just going to introduce a scalar here that I will call t. So what that means is it goes from O to A and then it goes in the direction of B. It can also go this way if the scalar t is negative. So OA is simply the vector from the point A minus I plus 2j. And then we have our t. Now the vector A to B is just B minus A, end point minus start point. So that will be 3I minus 2j plus k. So this here is our final answer. Now we're essentially doing what we did when we used to find the equation of lines. So a line is a set of infinitely many points, and we'd come up with an equation like y equals x plus 1 to characterize all the points on the line. And we've done that here. This characterizes all the points on the line. Each of these infinitely many points lying on the green line can be written in this way for some value of t. Different values of t yield a different point. All right, let's now look at another example. So we're now going to take that line from the previous slide and we're going to write its equation in parametric form and then into Cartesian form. So this line here, the vector equation of that line, tells you how you can express any point along the line as the sum of this vector and a scalar multiple of another vector. So when we're writing it in parametric form, we're basically figuring out how you could find a point on the line just from the value t. So to do this, I'm simply going to expand the brackets here and collect like terms. So leaving the negative I plus 2j alone, I'm going to expand the brackets. So I get 3ti minus 2tj plus tk. So collecting like terms, we'll collect the i's together. I have 3t minus 1i plus 2 minus 2tj, and then the k is by itself. I'll leave that alone. So here we have that the x component is equal to 3t minus 1. The j component or the y component is 2 minus 2t, and the z component is just t. So this is said to be in parametric form. We've written x, y, and z in terms of another parameter, in this case t. So in this form, you just need to know the value of t. You can substitute into each of these formula, and you get the x, y, and z coordinate of a point that lies on the line that was on the previous slide. So for the Cartesian form, we want an equation linking x, y, and z. And we can do that from the parametric form because they all involve t's. So we know that z equals t. So let's start with that. I'm going to here rearrange this to get t in terms of x. So to do that, I would simply add 1 and divide by 3. That equals t. And doing the same with the y coordinate, I would subtract 2 and divide by -2. And that would also give me t. So now we have each of these equal to t. So we must have that x plus 1 on 3 is equal to, I'm going to times top and bottom here by -1, just to make it look a bit nicer. And that's just equal to t, which was also equal to z. So this gives us slightly different information than either of the previous two equations. It tells us that any point on that line that I showed you on the first slide has x, y, and z coordinates that satisfy this equation here. All right, now that we know how to write the equation of this line in 3 different ways, vector, parametric, and Cartesian form, let's look now at calculating distances. So we're going to calculate the distance between this line that we had before and this point. So I'm showing you here how to find the distance between a point and a line whose equation is given in vector form like this. So here A is that kind of initial vector and D is the direction vector. And that's what it means in these formulae. So the formulae for 2D and 3D are slightly different because in 3D we have the cross product and we don't really have a cross product in 2D. So here this means the y component of the vector from A to P. Now P is a point, but we're going to write it or treat it here as a vector in both of these cases. Similarly, this refers to the x component of the direction vector and the y component of the direction vector. But for this example up here, we need to use the formula for 3 dimensions. So let's get to using it. So here, P is the point 0, 1, 0. So as a vector, it's just j. So here, P minus A would be the vector j minus, we had for A negative I plus 2j. So that will give us I minus j. So we now need to calculate the cross product of I minus j and the vector d, which is this one here. So we would have the coefficient of j in the first times the coefficient of k in the second minus the coefficient of k times the coefficient of j. That will give us the I component. Then it's always a minus when we come to do the j component, so it's I times k, and then k times I. That will give us the j component, and then it's always a plus for the last one. So it will be I times j and j times I. So that gives us the vector negative I minus j plus k. So the absolute value or the magnitude of that is simply the square root of 1 squared plus 1 squared plus 1 squared, the sum of the squares of each of its components. It is root 3. So in our calculation, we've calculated that root 3 goes on top. Now on the bottom, 3i minus 2j plus k, that's our d vector. So its magnitude is the square root of 3 squared plus 2 squared plus 1 squared, which is the square root of 14. So this is just the square root of 3 over 14. And that gives us about 0.46 units. Now you might have wondered, why did we need the cross product here? When we're saying the distance between the line and the point, we're really asking for the shortest distance from this line to this point. And it turns out the shortest such distance is always the perpendicular distance from this line to this point. So what we had to do first, essentially here, we're calculating a vector that is perpendicular here and also goes through that point. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.